laptop plugged in so we don't run into problems like last night. Alright. Where's my face? Chatting. I'm gonna be chatting for a little bit. Chatting. Oh, I see a person. I see someone join. So what are we gonna do today? Today we're gonna be continuing what we were doing yesterday. Namely, using some awesome Linux tools to process packets very efficiently. Manage your channel directly from your phone. That's what I need. That's what I'm holding my phone over here. All right. No changes for me. Okay. I see. Yep. Perfect. Let me set this up. So I have my laptop on charging over here. See the messages. Now I'm gonna pull up the do not disturb. All right. What are we gonna do? I was just listening to music. It was so good. So it turns out it's very hard to find good music for a Twitch stream. I don't want to just play some random Creative Commons music. I don't know if it's gonna be good. I can't play my music either. What was that? Wow. This the sound of follow on Twitch always freaks me out. All right. Oh, I don't think I'm logged into Twitter on my laptop. Oh, I am. Yes, I am. Anyhow, what are we gonna do today? Well, first of all, I gotta start sharing my screen, I suppose. There we go. Oh. All right. Logistic regression. That's for another day. Homework. Blog posts. GitHub. Might have to log in. Might have to. Ooh. All right. Where are we going? We're going into XDP tutorial. All right. Okay. So last time I was doing first packet processing lesson with XDP and eBPF, and as a reminder, that means we can write limited C code that then gets compiled and loaded by the kernel and this micro virtual machine, and the code gets executed right as soon as the Linux kernel gets a packet off of the wire, so we can attach some code to a network interface, literally almost to the hardware, and do some packet processing before the kernel does anything to it. So, and that enables us to process or forward or drop packets very efficiently. So what we're doing yesterday. Last time. So we have this little machine. I got four different virtual machines, just because I'm doing some network setups for practice, and one of them I'm using for this networking programming stuff. All right, and as a reminder, this very cool GitHub repo. Who's Net Optimizer? Let's see. Has a bunch of lessons teaching you how to use XDP and do all this super efficient packet processing. I guess it doesn't work. Right. So last time we actually wrote some code to inspect packets, and so we on the entrance we get the literal Ethernet packet, right? And then we parse it and we check that it's a legitimate Ethernet packet. We look at the head. We then looked inside the IP header. Then we looked inside. Then we were expecting to see ICMP headers, but default, everything that's not ICMP, we're just letting through. With ICMPs, we're dropping every other packet with our that hits our network interface. And I got it to work last night, but there were problems, and I fixed some bugs earlier today, and I believe now it should be all working. CD test. Let's see what we did last time. Let's see what we got working. Let's make it. Let's do T setup. So this is just a helper script that's aliased by T. So it helps me do this setup, and once I hit the setup, I can look at, I can look at IP link and see that I have this interface over here, and that it leads into, it connects in network namespace that the script sets up for us. So, and then I could run tping, and this would be sending pings ICMP packets from inside the network namespace to the outside outer side of the V pair, right? Okay, so what were we doing? We need to do tload. This just, so we compiled our program, now we loaded it, now it's attached to the network interface, and now we're gonna take a look at tstats. Tstats, this code. So tstats runs a user space program that pulls some statistics from the kernel extension that we wrote. And so we can see that there is nothing flowing. So we're going to do tping, send some ICMP packets, right? Send some pings toward this address over here. And we can see, and you can actually notice that the ICMP sequence skips every second one, every other one, right? Now, why is that? That's because we decided to make it do so. So if we now look at these stats, we're gonna see that every other packet gets dropped, right? Perfect. We see that there are 4 drop packets, there are 5 passed packets, and that's pretty much what we saw over here. Beautiful. So it all works. Let's move on to the next problem. See what's in for today. Rewriting. Oh man. Ooh. What are we doing? I wish I could play some music. Having completed the packet parsing lesson, and you're now familiar with how to structure. Oh wow! I almost spilled my water onto the laptop. You know what I wish? I wish that one day MacBook front cameras won't be as shitty as they are today, because the video quality is just terrible. So this is the code we're going to be working with today. It looks like a lot of, exciting stuff. I'm thrilled. Do proper bounds checking. And how did it predict? There are some things I actually didn't understand from last time, namely the network to host order when called on the IP packet next header field was causing problems. I don't know why, but anyway, we saw in the previous lesson. First perform correct bound. Oh, this is actually fun, right? So we need to, we'll look at our old code. We need to do this bound checking, and the verifier checks that we do the bound checking when we load the program. We attach a program to a network interface. without it, we wouldn't be able to access the packet. Displays not the data reads, but also to writes, which means that we can rewrite packet data simply by changing the memory it occupies. We'll use this in the assignments below to modify packet header fields. Fantastic. Ooh, we could I don't know, do some. Imagine you could do some of your own encapsulation with this in a very efficient way. Probably wouldn't be as efficient as some native tools available for it, but you know, you should never limit yourself. While many things. Oh, whoa! I called it. Sometimes it's necessary to add or remove chunks of memory entirely, for instance, to perform encapsulation or to remove product headers from a packet. The kernel exposes an eBPF helper function to achieve this, which is called BPF XDP. It just had. Let's take a look at it. There's probably better documentation than this explanation. Adjust move data. So right, every time our program gets called, what do we get as an input? As an input, we get this wonderful structure called context, and essentially describes the packet. So we have data. It's a pointer to the start of the data end, and then data meta is just some space we can use to store some information that we ourselves need. I think haven't used it yet. Anyway, all right. This is the interface index and the queue index. Receive queue index. Sometimes wobbly. Just move, but delta bytes. Note that it is possible to use a negative value for delta. This helper can be used to prepare the packet for pushing or popping headers. A call to this helper is susceptible to change the underlying packet buffer. Therefore, at load time, all checks and pointers previously done by the verifier are invalidated and must be performed again. If the helper is used in combination with direct packet access. All right, this makes sense. This is what they just told us. XDP, and then the adjustment size as parameter, and we'll move. I love that function interface is so simple. Just the structure and an integer. Ooh. 1 second. What's going on? Right. There are a few things to be aware of when using this helper. First, it may fail either because the adjustment will make the packet data too small to contain at least. There's not enough space in memory before the start of the packet. The helper only adjusts the data pointer. It is up to the XDP program to ensure that the packet data is valid afterwards. This typically involves rewriting the ELR in a header, then you start the packet location adjusting. Yep. Finally, the verifier will discard. Wonder if. Alright. We'll discard all information about previous balance checks after the packet size has been adjusted. Yeah. Listen, we just tried. So, see, you always want to go to the primary sources for scientific information. You don't want to read this here. You want to read this here. The man page, the manual page, rather than the guide on GitHub. The manual page is always better. Always better. There is also, which can be used to, so by now, Oh, and we can do the same with the end of the data, the end pointer. All right, all right, all right. In this lesson, we'll be creating two programs. One that rewrites the destination port number of TCP and UDP packets to be one less than its original. Whoa! Are you feeling the magic yet? A packet that is being sent to port 8080 can be redirected to port 8079. Well, I mean, it's not being redirected anywhere because it's still the same network interface. It's just up to the layer 4 here how to interpret it. But and another that removes the outermost VLAN encapsulation header if one exists, or add a new one if it doesn't. All right, so the VLAN is something I'm working on, but we'll get to it. Let's have fun with the first assignment first. You know, gotta do things in order. I'm trying to pull up the chat, which is empty, which is not a problem. Welcome to the chat room. Can I send an emoji? Whoa, there are stickers. Who are these people? I don't know what's up with all this meme culture. Not my vibe. What are all these faces? I'll send a football. There we go. Football. All right. We're gonna rewrite port numbers. For this assignment, you'll need to parse the TCP. Let's see what code we got as an input, right? So every time they give us some code to work with, and let's see. Where's our main? Oh, I'm an idiot. This is so okay. So let's do what we're gonna be working with. Again, as a reminder, we can have multiple XDP programs within one file here. It all gets compiled and get one ELF file as the output. Then we get it loaded, and then we get it. We specify the particular program to attach to an interface. I wonder what would happen. Like, I don't think you can attach multiple programs because you don't know what order it would execute on. And it's solution to the parsing exercise. No, I don't want solution. Oh, in lesson packet 01. Let's actually take a look at it because that's something I was doing last night. As a reminder, I love that they call IPv4 legacy IP. So, you know, the exercise first asks you to handle IPv6, and then we're like, yeah, we gotta support legacy IP addresses IPv4. That's the right way to think about it. Default action XDP pass. Yeah, we've read it all. Keep track. Yes. Packet parsing in steps. We parse the Ethernet header. We check that it's IPv6 or IP. If not, then we just do the default action. We do the host to network order, byte order conversion here for this constant, right? So IPv6, so we parse IPv6, we check that the inside is ICMPv6, and oh, interesting. So if it's not echo request, we go to all right, and then we drop if it's even, and same stuff for IPv4, just different parsing function. All right. In VS Code, can I like search for a particular file? Whoa! Let's read Linux Torvalds code. Rewrite in simply a matter of right into the right field in the header. So this is the packet parser. All right. Where do we do the? This is the rewrite. This is okay. This is where we're gonna put our implementation. The rest is for later. Cool. All right. All right. Hmm. Hmm. All right. Okay. So here's what we're gonna do. We are gonna. So first we need to obtain our UDP or TCP packet, right? So for that, we cast our pointers to data start and data end. Oh my god. All right, we don't need any actions here. We do need the cursor. We don't need this. Uh-huh. And now we need to. All right. Yeah. Right, so after this. So first we parse the Ethernet header, so we have the Ethernet header, right? Next we do the same, and we want our IP header. Oh, come on. Oh, I need to do, it needs to differ based on the version. That's annoying. All right. And then what we're gonna do is we're gonna reuse some of the code that we got from last time. All right. If it's IPv6, then we got the IPv6 struct. We don't not care about ICMP this time, right? So we parse the IPv6 header. We got our IPv6 header, right. And this time we do not care about the next header type. Well, we do care about it, but right now we don't care if it's ICMP. We're actually interested. We're going to be interested in it being TCP or UDP, right? And same stuff here for IPv4. We don't need to parse ICMP. We don't need this check, and we don't need the drop. All right, cool. And if it's neither, need this, then we just return XDP pass. Cool. We always return XDP pass, but yeah, we can. No, I'm on. Oh, wrong one. All right, we're gonna do this out. We're gonna do this. Go to out. Just go away. All right. So yeah, we don't do any. Here's our setup. Cool, let's see. What? No, we just built? It's crazy. It's crazy. All right. Wait. Is it correct? All right, it is correct. Cool. All right. If it builds, it works. If it compiles, it correct. No. I think that's the Rust proverb. Huh. All right, so now we got our IP headers, and if you remember the packet encapsulation, we're interested now in, so where's this stuff? From link, we got the internet. From internet, we got IP. And now we need to get onto our transport layer, where all the interesting stuff happens. All right, so we'll need another helper function for it. Let's do it. So similar to this. Oh, who wrote this? Who wrote that? Where are you? Aw. All right, we'll just copy the declaration. I don't need this. All right. Parse. So this time IP header. Right. So we have next header type. Parse UDP. We're gonna need parse UDP. UDP header, and we'll need oneness, and we'll need the same parse TCP header. Cool. And oneness. And what we're gonna do? Let's the way I like to work with this is write the sort of the higher order functions first. So let's what are we gonna do? I need the list of these constants. No. IP header next header options. Oh, there we go. IPv6 packet next header. There we go. All right. So this is what we need. We need UDP for. All right. So we're gonna write some spaghetti code at first, and then if we're lucky, we're gonna refactor it. If nh type, same way we're doing it here. Let me. Come on. Where's the... Oh, there we go. All right, except for this is not what I need. What I need is this. What? Where's TCP? What are you doing? Oh. Feeling so slow. Oh. What do we compare to? Where's IP Proto UDP? Where's this defined? Come on, come on. No, what are you doing? I don't want iPhone. There we go. There we go. Finally. Protocol is the IP protocol in the IP header to be received or sent. Valid values for protocol include... cool. So we care about the IP prot underscore UDP and the IP... perfect, beautiful. Then we do UDP, else if TCP, and let's do this. All right, where's the UDP thing? UDP header. All right, perfect. Then we need struct UDP pointer up. And same way we need TCP. Where? No, it's not. Oh, there it is. Right. Want to see the header definition. TCP header definition. Right. Struct TCP header TCP. And this is what we're gonna have. Wonderful. And then we're gonna call, so we have these two functions. We're gonna get parse UDP header, or the arguments, the cursor, right, and then the data end. Whoa. How do we, right. Okay, because it doesn't change, all right. And we didn't rename. That's funny. All right. And we need here to. All right. Let's. No, we did. The fuck. Why are you? What? There's a function reading it for us? That's crazy. I didn't know there was a function for us. Whoa. Okay, so I guess we don't even need to write this. right? And what do we need there? Parsing. Oh, okay. Cool. Does it return this stuff actually? Oh, come on. It returns length. That's fair because it's the transport protocol. All right, let's do int len and int len. All right, and let's do this. All right. All right. Whoa, easy. I guess I can't even copy paste anymore. All right. Perfect. Use variable and use a declared identifier UDP where what? Because it's TCP and use variable. All right, we can. You know what? We will not need the variable. We might need it later, but I just want to compile it. Come on. Perfect. This works. We're 90% of the way there. So what we need now is to actually, we have our packets. We need to change the ports. So let's, whoa. Let's take a look. So, right, the source and destination, if the layer 4 in the OSI is responsible for the ports, so to speak. So the source and destination here are the port numbers. They're not IP addresses, of course. So there's 16 bits, right? So it goes up to 65,535. That's correct. We all can, gotta be able to raise 2 to any number. Okay. Now, if it's 16-bit, I shouldn't have to change that much. I just literally, all right, what are we doing here? So this is what they're doing for us. Let's understand this. All right, so we need to get the host order. Then when we subtract 1, subtract. There is no S. There is no second S. It's subtract. All right, and then we go back to network order. All right, well, okay. If you understand it, you can write it. So UDP dest equals, let's look, we'll need this help here. BPF, so on the outer, we're gonna go host to network, right? And on the inner, we're gonna go network to host of UDP dest, and here we subtract 1. Right, and that's pretty much it. And since it's allocated 16 bits, we don't need to move the header or anything. So that's pretty dope. So it's way simpler than I imagined. Way simpler. All right. The problem here, the problem here is that I can't code. All right. Looks like it works. All right, we got it. This should be it, right? This should be it. As far as I'm concerned, that's it. This is our function. This is our cute little function. Could be written better, but first try. So what we're gonna do is we're gonna t-load. We're gonna enter the super secret password that already typed incorrectly. Ah! Come on. There. Whoa! We've got a problem. We've got a problem here. Permission denied. Is this a joke? It's not funny. It should be suit. What? T-load. Let's do this a little more manually. Permission. What? Dev vice XDP tut 01E8. All right, we got an issue. Permission denied. That means we wrote some unsafe code. So see the verifier. So it compiles, right? But the verifier doesn't load the program because apparently it's not safe to load. See, it needs to be sure that we're not gonna take the kernel down. All right, what are we gonna do? Where is the problem? Oh wait, it doesn't know which one we're loading. Prog section, XDP port rewrite. What? Huh. That's wild. Do we understand why? That's not helpful. All right, let's look at this. He knows what the problem is. He knows what the problem is. I don't know what the problem is. All right, let's reread this stuff. Parse Ethernet header. So we parsed the Ethernet header. We got the Ethernet header. Next, we check that the inside of the Ethernet header we got the either IPv6 or IPv4. Good stuff. I don't see a problem so far. Here we have IPv6. Then we got our IPv6 header struct. We parse the header. We check that the type is either UDP or the following packet, right? So the encapsulation graph once again, or TCP. Good. Not seeing the problem so far. If it's UDP, then we get our UDP header. We parse it, right? The pointer, the cursor gets moved by the parse function always, right? It's always getting moved. Are you getting moved? Well, all right, not here because it's no, it does good. Yep. So, what's the problem? What is the problem? You know what? We're gonna cheat a little bit. Take a look at there's always the solutions. That's kernel 02. That's the one we're writing. All right. Nope, we're not patching ports. What? Nah. Solution to the assignment 1 and pack. All right. So we have the stuff. Okay. They parse the Ethernet header. How is this different from what I wrote? How is it different? Same stuff. Come on, people. Need hope. Need hope. Let's what for the purpose of debugging, we're gonna do what no one ever should be doing. This is illegal. Copying this whole code over here. Alright, so this time it would have worked. It's not cool. So there is a problem with our code. Let's clean it up. When there is a problem and when there shouldn't be one, you can always clean it up and make it a little easier to understand. In my experience, it works at least 10% of the time, which is a pretty good statistic when it comes to, writing C code. So, all right. Yeah, let's get all our structs declared over here. I wish there was music. TCP header. All right, we don't need it twice, right? So let's remove this, and IP header we already have. No, we have IPv6. Okay. Let's make it in pairs like this. All right, and this stuff. All right. Cool. So parse the Ethernet. We go to out. Oh, do we do the bounds checking? What? Let's yeah, let's do that. One reason to hate VS Code. Where am I? Where am I? Where am I? What? There we go. Aborted is the same as drop. It just but there is also an exception that we can track. Right. What's next? If we're good with the Ethernet header, then we. Whoa, 7 people. That's a lot. That's a lot. That's a lot of pressure. That's a lot of pressure. Next, we need to get the IP type, right? So what they're doing there is, right. So they're doing. I'm essentially just refactoring what I already have. Ha! 1 second. So, why am I using long here and short there? Is it because why? Yeah, why am I? Let's give this a try. Let's see if anything changes. Variable action isn't it? Is used initialize. Line 74, variable. No. I don't like this. I don't appreciate the verifier. All right, let's quick sanity check. So if we have IPv6, then our IP type, right? Where's the IP type? We'll need IP type. Is going be coming from this stuff, this code over here. This is the IP type now, right? And we don't need this anymore. Else if type equals BPF just IP, meaning it's IPv4, then the IP type uses the legacy IP header parser, meaning it's IPv4, and I don't see the arguments, and now I see syntax highlighting, getting under my skin. Come on. Easy there. Alright, so, and we will not need this either anymore. Let's just wipe it out. Do we need this check? I don't know. Do we need this check? Well, we certainly do need this. What about the IP type check? Well, it's fair. We just compare it to if IP type equals IP proto UDP, we do the UDP parsing, else if IP type equals IP proto TCP. We do the TCP parsing, else we go to out and don't do anything. All right, cool. And what does the parsing mean? That means that here we call this, here we call this, and then here we do this, and here we do this, and that's pretty much it. Much cleaner code. So essentially all the time except this time when we have a legitimately invalid packet, we just, you know what, I think this thing can return, it returns, it doesn't, no, it can return -1. You know what, if it's else if, we're just gonna add a little check over here. Action equals XDP upwarded. Go to out. Else go to. Our code is going to be better than the solution code. And then let's see. What are we doing here? We're looking at this, and this comes from here, and this stuff. Yeah. We've done the check there. Okay. I'm just going to return this. Remove. And right. All right, this is what I got. Use typos. Who made the typo? That person has to face serious repercussions. Line 94, line 94, line 94. Oh, whoa, that's not a semicolon at all. Line 96. That is not go to. T-load, please. What? All right. That's a travesty. You know, why didn't it load? Oh boy. All right, let's try this. We're gonna comment this out and see if it works this way. And it did work. All right. So the problem is here or here. And let's take a look. Let's take a look. Does anyone, this is called find differences. I don't see, am I blind? I don't see a problem. Ah. What if it's okay? Ah. Oh. It's because of this check. It's because of this check. It's because the verifier is very, very clever. It's very, very clever. And the verifier is very, very clever. So what I need to do, if right action equals XDP imported go to out, and just like that, if we comment this out, it should start to magically work. Yep, exactly. All right. Cool. So we need to do the same here. Action equals XDP uploaded. Go to out. And now we can uncomment this, and now we're good to go. Let's just sanity check once again. Sanity check. I need some water. We duly check here. We duly check on the this, and we do all right. T load, and this time it should work as long as I do the T reset, T load, and it did work. We got success. So what I'm gonna do now is use the utility to what? SoCat sudo apt install SoCat. Yes. Oh. Artem, go work. You gotta work. Oh. What was it? I don't remember. Right, what do we have here? Doesn't. Oh. There we go. Whoa! Look, we got a packet going to 1999. 1999. See, we directed 2000, but it is being seen as a packet sent to 1999 on the receiving side, because just as soon as the packet hit the network interface, we rewrote the destination port and lowered it by 1. Just as a double check, we can go to 2001 here and do send, and then we see that we got to port 2000. Milorida. Oh, hello. We got to port 2000. All right, cool. So this stuff works. So pleasant. Wait, what was that sound? Again, gotta pull this up. Got a follower! Crazy. Crazy. Alright, what's next? Remove the outermost VLAN tag. I'm gonna go read the textbook for this. You know what? I've been reading this textbook called Computer Networking from the ground up. It's a fantastic book. It's a fantastic book. It's a fantastic book that tells you everything you need to know about networks. Everything. Everything, including the algorithms they use for routing inside the autonomous systems and between the autonomous systems and anything you want to know, including the layer 2 chapter over here, which I haven't gotten into yet. So VLANs cause, irrational fear in me whenever I see the word. But all right, let's take a look. This assignment we will start implementing the program that removes the outermost VLAN tag if one exists. So again, the VLANs work by attaching a tag and the kernel faking this local area network separation. But because our processing is actually being done before the kernel removes the tag, we can actually identify the VLANs and right, because it's all hidden in the same interface one way or another. Cool. Which means that, whoa, I don't like that sounds. Hello. That's funny. To do this, fill in the VLAN tag pop function that is prototyped in XDP proc kernel. Oh my god, we don't need this anymore. Alright. Pops the outermost VLAN tag off the packet. If only I understood the VLAN tag hierarchy, it would have been better. And inline comments from our solution to the issue to guide you in the implementation. Alright. We got a lot of help here. Shouldn't be too bad. Once you've implemented the function, test that it works by setting. Alright, before we test, we need to have something to test. Whoa. VLAN, let's see multiple VLAN tags. Q&A, what is it? gtackknowledge.extremenetworks.com. This is exactly what we needed. I was dreaming of ending up on this website today. That on any given port you can have multiple tagged VLANs, but only one untagged. Oh. We'll send out a packet with a header. The port only has one VLAN. It's not required to stipulate what VLAN traffic the port carries. Alright. Okie dokie. But what about, I don't understand, how could there be multiple VLANs? Could I, like, VLAN on VLAN? Double VLAN. Opa! VLAN double tagging, that's what it's called. No, I don't want an attack. Oh, anyway. Computer security exploit a method of attacking network resources in a virtual LAN. The basic concept behind all VLAN hopping attacks is for an attacking host on a VLAN to gain access to traffic on another that will normally not be accessible. How do you do that? Switch spoofing and double tagging. Both attack vectors can be... Alright, so misconfigured switches always lead to a lot of trouble. Lots of trouble. Attacking host imitates a trunking switch. What do I? That must be trunking. Okay. Okay. Ooh. Right. Prepends to VLAN tags. Oh, there we go. There we go. Introduce the concept of double tagging. Double tagging can be useful for internet service providers, allowing them to use their VLANs internally while carrying traffic from clients that is already VLAN tagged. Woof. The outer comes first. What if there can be more than 2 tags? All right. Anyway, ooh. All right. We cast our pointers. Ethernet, okay. VLAN header. The check if there is a VLAN header to pop. All right, we've written this code before. We can do this. We can just copy it from the last time. This is what we're gonna use. We're not gonna need that. Alright. This is what we need. This is what we need. Header size. Header size. Well, alright. What's the better way to write it? Instead of this, we do the Are we gonna call it? I don't like this one. All right. What? We're actually... What? Oh, we gotta import it. All right, we got the header already. What? I'm an idiot. All right. Tload. Did I need to do tload VLAN plink? TP. Oof. All right, I'm gonna need help here from the solutions. Oh, we still need the cursor. No, this is the VLAN swap. I want to see the tag pub. Oh, come on, man. Oh. Oof. All right. Let's look. What are we doing first? Yep. Careful with the parentheses here. What are we doing? VLAN header. So we move by 1 and then we cast it, right? All right, let's get the VLAN header by moving. So this thing right here is gonna be, so we take the given Ethernet header, we move by its size, and then we cast it, right? Cool. We need to do balance checking. Let's look at this. All right, so this is the same balance checking we've been doing all the time, so there's nothing new here. Go to out. Looks all too similar to the first statements in Go, but say VLAN ID for returning. All right, so where's the struct we're talking about? All right, let's just copy it here just to have as a reference. All right. So what we're interested in is, taking the, what are we interested in? We're interested in VLAN ID being the network to host order, eBPF network to host order of the DLH, the TCI, the tag, right? Is that correct? That should be, what am I looking at? Nope. Pop. What? I lost it. Shite. There it is. Right. Right. And then we take the next proto. We copy the outer Ethernet header before we cut it off. Okay. And then copy block of memory destination. All right, so we're gonna get this into copy, and all right, that's fair. Size off. Okay, cool. Why are they doing this here? Actually adjust the BPF for this. Let's pull up the manual once again. So the first is the context and then the delta, and we move by the size of the header, right? So we copied it just in case we move. What's the return value? All right. Okay. And then we need to reevaluate data and do new bounds checking after it. All right, let's do it one by one. Okay, so what's next? So we change the H proto. And this time it's going to be VLH, this stuff. Then we do built-in mem copy, right? And what are we copying? We're going into destination, which in our case is going to be this guy, right? From source, which in our case is going to be this guy. And then we're going to be int size off. Is this correct? No one knows. No one knows. No one knows. No one knows. Should be. Looks like yep. And after that, after we've copied, what do? We use this beautiful function, and so if it returns, let's make a comment here. Return 0 on success. Go to out. Right. But whoa, we don't need to do this. That's me being stupid. It just had, so we passed the context, right? And we pass the delta, and this time it's going to be int, and we're interested in moving by the size of the header, so we're gonna do int size off this, right? Is this correct? Someone tell me it's correct. Well, except for what? All right, C syntax. You got me. And we need the value. All right, cool. Where did that happen? Oh, we needed it. And implicit declaration of function. No, it's not implicit declaration. It should be important. Where is this coming from? What are we using here? Yeah. All right, cool. What's next? So we popped the outer Ethernet header, and we moved the we adjusted the head of the packet by a little bit. So we popped the tag. What are we doing next? And assuming that all went well, so far we've done this. Just need to reevaluate data and do new bounds checking after adjusting head. All right, let's reevaluate. Because they told us we need to do this again, right? Call to this header helper is susceptible to change the underline. Therefore, at load time, all checks and pointers previously done by the verifier are invalidated and must be performed. So if we were to try and do like tload right now, it's gonna be should be arguing with me. Why is it not arguing with me? Should be angry. Well, T reset VLAN. Let's try to do it. Huh? Was it successful? Well, okay. Guess the verifier. Reevaluate data and then do new balance check. All right, so we're doing the same stuff we've done before. Is that correct? We have to. I see. Okay, so we need to do the same stuff. Wait, why are we doing? Why are you changing Eve? Okay, that makes sense. And we need to do data end. What is it? Oh. Whoa. Is it? I see. Let's use the same formatting. Need to. Right, so we need to check that the Ethernet headers fits. Right, that's correct. Go to out. Excuse me. All right. Copy back the old Ethernet header and update the prototype. Why do we need to do that? What are we doing here? Copy back the old Ethernet header. What? All right, this step I don't understand. What are we? Oh, so we're not actually changing anything. We're just popping the tag. No, that's not true. What are we trying to achieve? Someone tell me. What are we trying to achieve? Confusion. No, we're seeing the VLAN tags. Alright. Something's no good. Okay, I'll need to debug this. This is gonna be my follow-up tomorrow morning, as always. Right, this was fun. Back missing VLAN tag in this on the opposite of the previous one. Alright, I'm gonna read up on the VLANs today, because this doesn't make full sense to me. Okie dokie. Let's see where the stuff is. Alrighty. Gonna end this now, so I can play music without getting blocked.